Gravity pulls equally on heavy and light objects. Okay, let me ask you something. If you drop a hammer and a feather at the same time, which one hits the ground first? Be honest, most people would say the hammer, right? Because our brains are wired to think, well, duh, the hammer is heavier, so it falls faster. That feels so obvious that almost nobody questions it. But here's the thing. In the pure world of physics, where we strip away all the messy stuff like air, wind, or turbulence, both the hammer and the feather hit the ground at the exact same time. Crazy, right? Heavier doesn't mean faster. And that idea alone feels like it's flipping reality upside down. Now, why is that? It comes down to how gravity actually works. Gravity doesn't care how heavy you are or how light you are. It just pulls everything down with the same acceleration, about 9.8 meters per second squared here on Earth. That means if you're a bowling ball, a pencil, or even a grand piano, gravity is tugging on you with the same falling speed. So, if that's true, why do we see heavier things fall faster in real life? Because we're living inside a soup of air. That feather gets slowed down by all the tiny air molecules it's bumping into as it's trying to fall, while the hammer, being dense and aerodynamic, just bulldozes straight down. Air is the sneaky villain in the story, not gravity. And here's where it gets even cooler. Back in 1971, astronaut David Scott from the Apollo 15 mission decided to put this exact idea to the ultimate test on the moon. The moon doesn't really have air, no wind, no atmosphere, so it's basically the perfect vacuum testing ground. He took a hammer in one hand and a feather in the other, held them up at the same height, and dropped them. And what happened? They smacked the lunar surface at the exact same time. It was like the universe's mic drop moment. Now, think about that. If you ever believed heavier things fall faster, you're not wrong for thinking that way. Your eyes trick you because of air resistance. But deep down, nature is way more equal than it seems. Gravity is like that strict teacher in class who treats everyone exactly the same. No favorites, no exceptions. And this has some wild everyday connections, too. Like if you crumple up a piece of paper into a tight ball and drop it next to a notebook, the paper ball falls almost as fast. Why? Because you got rid of its air-catching shape. You made it harder for air resistance to slow it down. So now gravity can show off its true equal treatment. Here's a fun thing you can try at home. Take two different objects, say a shoe and a spoon, and drop them at the same time from the same height. You'll see they land almost together. Not perfectly because air still plays its games, but close enough that you'll realize, oh, wow, this gravity thing is not about heavy versus light. It's about strength versus drag. And if you think about superheroes like Superman, this is exactly the kind of science that makes his powers interesting. He doesn't just defy gravity by being heavy or light. He does it by having enough strength to overcome air, gravity, and physics all at once. If Superman dropped a car and a coin from the sky, they'd fall the same. He'd have to use his insane strength to catch them both before they smash into the ground. So next time someone says, heavier things fall faster, you can smile and say, not really. Gravity plays fair. It's air that cheats. And that little shift in how you see the world makes you feel like you just unlocked a secret rule of the universe.
Escape velocity isn't about strength. Okay, imagine this. You're standing on the ground, flexing like you're about to do the world's biggest jump. You crouch down, launch yourself into the air with all your strength, and what happens? You go up, maybe a meter or two, and then, bam, gravity pulls you right back down. No matter how strong your legs are, you're not getting into space with the jump. And that's because leaving Earth is not about strength, it's about speed. More specifically, it's about something called escape velocity. That's the magic number you need to reach if you want to break free from Earth's gravity completely. And that number, it's about 11.2 kilometers per second. Now let's pause for a second. 11.2 kilometers per second. That's not just fast, it's mind-bending fast. Imagine driving your car at full highway speed, like 100 kilometers an hour. You need to go 40,000 kilometers an hour to hit escape velocity. That's basically fast enough to go around the entire Earth in just over an hour. Yeah, good luck trying to hit that with your quads on leg day. So what does escape velocity really mean? It's the speed you need so that Earth's gravity can't pull you back down. Gravity is like an invisible leash tied around you. If you go slow, the leash yanks you right back. But if you sprint fast enough, you snap the leash entirely and drift off into space forever. And here's the kicker. You don't have to be Superman strong to escape Earth. You could be a tiny rocket the size of a backpack or a giant spaceship the size of a building. As long as you reach that speed of 11.2 kilometers per second, you're gone. That's why astronauts don't have to be bodybuilders to leave Earth. It's the rocket engines doing the job, not muscle power. Here's a fun thought experiment. What if Superman tried to escape Earth without flying, just by jumping? Even with his super legs, it's not strength that would get him there. It's whether his jump could give him the right speed. If he could somehow push off the ground fast enough to hit 11.2 kilometers per second, he'd leave Earth in a single bound. But if he only managed, say, 5 kilometers per second, gravity would still win, and he'd eventually fall back down just like a giant cannonball. That's actually how rockets work. They're not muscling their way into space. They're basically riding giant controlled explosions, accelerating faster and faster until they hit that magic speed where Earth just can't keep up anymore. And once they cross it, they're free. That's why every rocket launch is about speed, not about how heavy the rocket is. And here's something most people don't realize. The size or weight of the object doesn't matter when it comes to escape velocity. Whether it's a baseball, a satellite, or a spaceship, the speed is the same, 11.2 kilometers per second. Of course, the heavier the object, the more fuel or energy you'd need to push it up to that speed, but the rule itself doesn't change. Want to know something even cooler? Escape velocity isn't the same everywhere. On the moon, the escape velocity is only about 2.4 kilometers per second. That's like 5 times slower than Earth, which means if Superman wanted to jump off the moon, he wouldn't even have to try that hard. Even a giant cannon could launch an object off the moon into space. On Jupiter, though, forget it. The escape velocity there is a ridiculous 60 kilometers per second. You need a rocket so powerful it'd make our current tech look like fireworks. And this matters for more than just space travel. Think about meteors. When you see a shooting star burning across the night sky, that rock didn't just casually drift toward Earth. It's flying at insane speeds, way above escape velocity from wherever it came from, which is why it could even reach us in the first place. So the next time you see a rocket launch, or even a movie where Superman flies off into space, remember this. It's not raw strength that beats Earth's pull. It's hitting that magic speed limit. Muscles won't do it, sprinting won't do it, even jumping like the Hulk won't do it. If you want to leave Earth behind, you need speed. Lots and lots of speed. And here's a fun way to visualize it. Imagine throwing a baseball. If you toss it lightly, it arcs and falls right back down. Throw it harder, it goes farther. Throw it insanely hard, and it keeps going, looping around Earth in orbit. But if you could somehow throw it at 11.2 kilometers per second, congratulations, you've just yeeted that baseball into space, never to return. So yeah, breaking free from Earth isn't a matter of heavy or light, or even strong or weak. It's a matter of speed. 11.2 kilometers every single second. And once you hit that, gravity has to let you go.
Gravity is the weakest fundamental force. All right, let me blow your mind for a second. Gravity, the thing that holds you in your chair right now, the thing that keeps planets orbiting the sun, the thing that makes black holes the most terrifying monsters in the universe, is actually the weakest force we know of. I know, that sounds insane. How can the weakest force be the one that literally controls galaxies? But it's true. Let me put it into perspective. Take a simple magnet. You know, one of those little fridge magnets holding up your grocery list. That tiny piece of metal has enough magnetic strength to pick up a paperclip. And in doing so, it's beating the entire gravitational pull of the Earth on that paperclip. Think about that. One dollar store magnet versus the whole planet, and the magnet wins. That's how weak gravity is when you compare it to other forces. So why is gravity still the boss on the big scale? Well, it comes down to one simple trick. Gravity never cancels out. Let's break this down. In the universe, we have four fundamental forces. There's electromagnetism. That's your magnets, electricity, lightning, all that good stuff. There's the strong nuclear force, which holds the inside of atoms together. There's the weak nuclear force, which is involved in radioactive decay. And then, finally, there's gravity. Out of all of them, gravity is the absolute wimp. But here's the catch. Most of the others can cancel out. Positive and negative charges, they balance each other out. Magnetic north and south, they can neutralize each other. Even inside atoms, forces balance perfectly. But gravity, it doesn't have a negative side. Mass only pulls. There's no opposite anti-gravity charge that cancels it out. So even though it's the weakest, it just keeps stacking and stacking and stacking. That's why you don't feel the strong nuclear force every day, because it's locked up inside atoms. You don't constantly feel electromagnetism pulling you around either, because positive and negative charges usually balance each other out. But gravity, it's always there, quietly adding up, every atom of Earth pulling on every atom of your body, never giving you a break. And when you add it up on a cosmic scale, it's unstoppable. Every star in a galaxy pulls on every other star. Every planet tugs on every moon. It's like this endless cosmic teamwork that never cancels out. That's why galaxies spin, stars form, and black holes exist at all. Here's a fun way to picture it. Imagine you're at a stadium with 50,000 people. Everyone whispers, "Gravity, gravity." Individually, each whisper is weak. You could ignore one person whispering in your ear. But when 50,000 people whisper at once, it becomes deafening. That's gravity. One atom pulling on another atom is nothing, but trillions upon trillions of atoms pulling together? That's how you end up with planets, stars, and galaxies. And here is a quirky everyday reminder. Your own body has its own gravity. You are literally pulling things toward you right now. It's just so ridiculously weak compared to Earth's pull that you'll never notice. But technically, the pen on your desk is attracted to you ever so slightly. You and your chair are gravitationally bonded, just a little. Kind of romantic if you think about it. Now, let's tie this back to superheroes for a second. If gravity is the weakest force, Superman doesn't actually need to fight it with brute strength. In theory, if he could manipulate any of the other forces, like electromagnetism, he'd absolutely crush gravity without breaking a sweat. A single lightning bolt is already 1,000,000 times stronger than Earth's gravity in raw force. That's why Superman lifting buildings is flashy, but scientifically, there are weird ways to beat gravity if you control the stronger forces. But gravity wins in the long game. It's weak, but it's relentless. It doesn't shut off, it doesn't cancel, and it doesn't need balance. Over billions of years, that tiny pull shapes the entire structure of the universe. So the next time you drop your phone and curse gravity, remember this. It may feel like the boss of your life, but in the league of forces, gravity is the underdog. It just happens to be the underdog that never gives up. Strength can counter gravity. All right, let me throw a question at you. Have you ever stood at an airport, looked out the window, and thought, there is no way that giant hunk of metal is going to fly? Seriously, airplanes are massive. A Boeing 747 can weigh around 400 tons fully loaded. That's like trying to throw an apartment building into the air. Yet somehow, this mountain of metal lifts gracefully into the sky. So what's going on here? Do planes somehow ignore gravity? Are they magically lighter in the air? Nope. The truth is way cooler. Planes don't beat gravity by being light. They beat it with strength. More specifically, the strength of something called lift. Here's how it works. Gravity is always pulling that plane down, no matter what, but those giant wings are shaped in a really clever way. When the plane moves forward, air rushes over and under the wings. Because of the wings' curved shape, the air on top moves faster than the air underneath, and faster moving air creates lower pressure. Boom! You've got higher pressure under the wing and lower pressure on top. That difference? That's lift. Lift is basically an upward force strong enough to fight gravity. The faster the plane goes, the stronger the lift becomes until, whoosh, the plane is climbing into the sky. And this isn't about weight, it's about balance. As long as the lift force equals or beats the pull of gravity, the plane stays up. If lift drops below gravity, the plane sinks. That's why when a plane slows down too much, like right before landing, the wings can't make enough lift and gravity wins again. Now, let me paint a picture for you. Imagine holding your hand out of a car window while driving. Tilt your hand slightly and you feel it push upward. Congratulations, you just made lift with your own hand. That's the same principle that keeps massive planes flying. Your hand can't carry you off the road, but scaled up into a giant metal wing, that's strength overpowering gravity in action. And here's the fun part. Gravity doesn't change. It's not like the Earth suddenly decides, oh, hey, this plane is too cool. Let me go easy on it. Nope. Gravity pulls the same way whether you're a feather, a hammer, or a jumbo jet.
It's all about how much force you can generate to push back. That's why a plane weighing hundreds of tons can still fly. It simply makes enough lift to counterbalance that weight. If you think about it, this applies to more than just planes. Helicopters don't glide like airplanes, but their spinning blades are just mini wings generating lift in circles. Even birds do this. Their wings flap to create enough upward force to resist their own weight. And hummingbirds, they take it to another level, beating their wings up to 80 times per second just to hover in place. They're not magically lighter than air, they're just strong enough to keep pushing back against gravity. Here's something that blows people's minds. If you took a plane to another planet, its ability to fly would change. On Mars, where gravity is weaker and the air is thinner, a regular airplane wouldn't get enough lift because the air density is too low. That's why NASA had to build a special little helicopter called Ingenuity to fly there. It had oversized blades spinning super fast because it needed to generate way more lift than a normal helicopter just to counter Mars's thin atmosphere. And it's not just science fiction either. Superman flying? If you imagine it scientifically, he'd need to generate some kind of lift or thrust strong enough to beat gravity, not just be light. Even superheroes need physics to make sense. So the next time you see a plane glide overhead, remember, it's not about the plane being light or somehow ignoring gravity. It's about raw strength. Those wings are basically invisible muscles pushing up with so much force that gravity doesn't stand a chance. Superman's leap makes sense. Picture Superman in your head right now. Chances are you see him soaring through the clouds, fist forward, cape flapping, basically treating the sky like his personal highway. But here's a fun fact most people don't know. Superman didn't originally fly. Nope. When he first appeared in the 1930s, he could only leap, and not just any leap. He could jump 1/8 of a mile in a single bound. That's about the length of 14 football fields in one hop. Sounds ridiculous, right? But here's the thing. It actually makes sense if you think about gravity and strength. Let me break it down. When you jump, you're doing the same basic battle with gravity as Superman. Your legs push down on the ground, and the ground pushes back, launching you upward. Gravity immediately starts pulling you down, and pretty quickly you're back on Earth. But if you had enough strength, more muscle power than gravity could handle, you could jump insanely high and far. That's literally what Superman was written to do. So why was this believable back then? Well, his creators, Jerry Siegel and Joe Shuster, imagined Superman as a man from another planet with a denser body and stronger muscles than humans. On Earth, with our weaker gravity, he'd be like a superpowered athlete who could casually jump buildings in a single leap. Kind of like comparing an ant to us. Ants can carry 50 times their body weight and climb walls like it's nothing. Not because they have magic powers, but because their strength scales differently compared to their tiny mass. It's the same principle that made Superman's leap sound scientific in the 1930s. He wasn't floating or magically flying, he was just really, really strong, using raw muscle to overpower gravity's pull. Here's a fun way to think about it. Imagine you're on the moon, where gravity is about 1/6 of Earth's. Suddenly, you can jump way higher, maybe 3 meters straight up, without even trying. On a planet with weaker gravity, humans would look like superheroes. Now flip it. If you had superhuman strength here on Earth, you could treat gravity like it's weaker for you personally. That's Superman in action. And if we look at the numbers, it's even cooler. To jump 1/8 of a mile high, Superman would need to launch himself with a takeoff speed of about 200 kilometers per hour, just from his legs. That means his muscles would need to generate thousands of pounds of force in a fraction of a second. Sounds impossible for us, but for a Kryptonian on Earth, totally in the comic book ballpark. Of course, as Superman comics evolved, leaping started to look kind of awkward on the page. You don't want your hero just hopping around like an Olympic frog when you could have him majestically soaring through the sky. So the writers upgraded him from incredible leaper to full-blown flyer. But that original detail is fascinating because it's one of those times when comic book science actually had a little logic hidden in it. And here's the part that makes you go, huh, that kind of works. There are real-world animals that do something similar. Kangaroos, for example, use powerful leg muscles to bound incredible distances. Fleas can jump 200 times their own body length. If you scale that up to human size, you'd look a lot like early Superman, leaping over tall obstacles, not flying, but covering insane ground in a single bound. So next time you picture Superman casually floating in midair, remember, originally, he was more like the world's greatest parkour athlete. His battles with gravity were all about strength, not magic. He wasn't defying physics, he was just flexing harder than gravity could pull. And honestly, that version of Superman almost feels more impressive. No cheap flight hacks, just raw muscle versus the pull of the Earth. A straight-up strength contest with gravity, and he wins every time.
Gravity doesn't cause pressure. Let's clear up a little confusion people often have. A lot of folks think gravity is what creates pressure. But that's not exactly true. Gravity pulls, but it's weight that causes pressure. And the only reason weight even exists is because gravity is pulling on mass. Okay, let's slow it down. Imagine you're holding a heavy backpack. What do you feel on your shoulders? Not gravity, but the weight of the backpack pressing into you. Gravity is just the invisible hand pulling the backpack downward. Weight is the result of that pull. And pressure? That's what happens when that weight pushes against a surface, like your shoulders. Here's a simple experiment you can try. Take a big textbook and press it against your hand. You feel the pressure, right? Now, take the same book and balance it on your palm, flat. Suddenly, it doesn't feel as bad because the weight is spread out over a bigger area. That's pressure in action. Weight divided by the surface area it pushes on. That's why high heels sink into grass, but sneakers don't. Same person, same gravity, same weight, but way more pressure under that tiny heel tip. Now, here's the key. How much pressure you can handle doesn't just depend on the weight. It depends on your strength. Imagine a strong man carrying 200 kilograms on his shoulders. His muscles, tendons, and bones have enough strength to resist that pressure without crumbling. Now give that same load to a regular person, and gravity hasn't changed. It's still pulling the same way. But the difference is strength. If your body isn't strong enough to resist that weight pressing down, you fold. You see this all over nature. A giraffe's heart, for example,
has to be insanely strong because it's constantly fighting pressure. Gravity is pulling blood downward all the time. So to push it back up to the brain, the heart has to generate massive force. If it were weak, the giraffe would just pass out every time it lifted its head. It's not that gravity changed. It's that the giraffe's strength has to rise to meet the challenge. Here's another wild one. At the bottom of the ocean, the pressure is crushing, literally tons per square inch. That pressure doesn't come directly from gravity. It comes from the weight of all that water stacked on top of itself, being pulled down by gravity. And yet, there are creatures living down there that survive just fine. Why? Their bodies have adapted enough strength at the cellular level to resist being crushed. You and I would be pancake soup at that depth, but to them, it's normal Tuesday. And if we swing back to humans for a second, this is why strength training is such a game changer. Your muscles aren't just for looking good in a mirror. They're literally your shield against weight. Every squat, every deadlift, every push-up is basically you saying, "Okay, gravity, I know you're pulling down, but I've got the strength to push back." Gravity is constant, but strength decides the outcome. Think about Superman again. He's not immune to gravity. He just has absurd strength to resist pressure. If he picks up a collapsing building, it's not that gravity has vanished. The building is still weighing down with thousands of tons of pressure. Superman just has the muscle power to fight back without crumbling underneath it. So the next time you feel that pressure, whether it's your backpack straps digging into your shoulders or the ache in your legs after standing all day, remember this. That's not gravity itself crushing you. That's weight, the middleman between gravity and your body. And the only thing standing between you and getting flattened? Your strength. On Jupiter, you'd weigh 2.5 times more. All right, let's play a game of what if. Imagine you step off a spaceship and boom, you're standing on Jupiter. First problem, you can't actually stand there because Jupiter is a giant ball of gas with no solid surface. But let's pretend for a second it had a floor you could stand on. What would happen to you? Well, the very first thing you'd notice is your weight. On Earth, maybe you weigh 70 kilos. On Jupiter, same body, same mass, but now you'd weigh about 175 kilos. That's almost like carrying 2 extra versions of yourself on your back. Every step would feel like a workout. Just lifting your arm would take effort. Your legs would feel like concrete. And jumping? Forget it. You'd barely get off the ground. Here's the important part, though. It's not gravity itself crushing you. It's the weight your body suddenly has under Jupiter's stronger pull. And here's the twist. If you had enough strength, you could still stand tall. It's just a matter of whether your muscles, bones, and heart could handle that extra load. Think about weightlifting for a second. If you squat 100 kilos at the gym, you're basically simulating a little taste of Jupiter gravity. Your legs are saying, "Okay, gravity's heavier now, but I can push back." Stronger legs, stronger back, stronger core. They're all about resisting weight no matter how much gravity is cranking up the difficulty. So technically, if Superman, or even just a super strong human, set foot on Jupiter, they wouldn't collapse. They'd just walk around like it's leg day, every day.
Now, here's a cool real-world connection. Astronauts train for this exact kind of thing, but in reverse. When they go to space, gravity basically turns off, and their muscles stop fighting weight. That's why astronauts lose muscle and bone density so quickly. Their bodies aren't resisting anything. It's like the opposite of Jupiter training. So what do? They work out 2 hours a day up there just to trick their body into thinking gravity still matters. Otherwise, when they come back to Earth, they'd be way too weak to even stand up. Let's get back to Jupiter. Imagine carrying a backpack filled with twice your body weight strapped on 24/7. Sitting down, standing up, even breathing would take more effort because your chest muscles are under pressure. Most humans would crumple, but someone with insane strength could still function. It's not impossible, it's just hard. And this is the part where you really see how much strength versus gravity matters. Gravity never changes who you are. Your mass is the same, whether you're on Earth, the Moon, or Jupiter. What changes is the weight you have to resist. On the Moon, you weigh 1/6 less, so you're basically a superhero compared to here. On Jupiter, it's the opposite. You'd feel like gravity just threw you into hard mode. Now imagine Superman landing on Jupiter. Everyone else would be crushed into the ground, but he'd stand there, cape fluttering like it's no big deal. Why? Because his strength is so over the top that 2.5 times gravity is just another day for him. It's not that Jupiter's gravity disappeared, it's that his muscles are powerful enough to push back against it without breaking a sweat. So here's the takeaway. Gravity sets the rules, but strength decides whether you can play the game. On Jupiter, most of us would lose, instantly. But with enough strength, you'd still be standing, looking around, and maybe even taking that heroic first step.
Olympic lifters versus astronauts. Okay, picture this. An Olympic weightlifter walks into the gym. Chalk on the hands, barbell on the ground. Plates stacked so heavy you and I couldn't even budge it. They take a deep breath, grab the bar, and boom, snatch it over their head like it's nothing. Everyone's clapping, people are filming on their phones, and this lifter looks like a superhero. Now, let's take the same person and drop them into outer space. No gravity, no weight, no up or down. You hand them the exact same barbell with all those plates on it. What happens? Well, nothing impressive. They can move it, sure, but it won't feel heavy. It's not going to resist them like it does on Earth. They could toss it away with a fingertip, and it would just float off like a balloon at a kid's birthday party. Their Olympic-level strength? Kinda pointless. That's the crazy thing most people don't think about. Strength only matters when you've got gravity pulling against you. Here on Earth, the lifter looks like a powerhouse because gravity is dragging everything down and they're pushing back. But in space, gravity isn't there to make things weigh anything. Without that resistance, all those muscles have nothing to fight against. It's like flexing your biceps in the pool. You feel strong,
But the water takes away the resistance, so your power feels like it's going into thin air. In orbit, it's even worse. Your body forgets what heavy even means. That's why astronauts in the International Space Station don't do bench presses or squats. They can't. The barbell would just float with them. Instead, they have to use special exercise machines with resistance bands, air pressure, or magnets just to trick their muscles into thinking they're still on Earth. And here's where it gets wild. Astronauts lose muscle mass frighteningly fast. Imagine you're the Olympic lifter again. You're used to moving hundreds of kilos. You spend 6 months in space, no gravity, no heavy weights. Suddenly, when you come back to Earth, you might struggle to even walk off the shuttle. Your bones get weaker, too, because they don't need to hold up your body anymore. It's like your skeleton says, "Oh, no gravity, cool, I'll retire." Meanwhile, the Olympic lifter on Earth is pushing their limits every single day because gravity never stops pressing down. It's like their permanent sparring partner. Without gravity, all that explosive strength doesn't translate to much. If they tried their signature lift in orbit, the bar wouldn't slam to the floor, the crowd wouldn't gasp, and honestly, it would look more like slow-motion yoga than world-class powerlifting. So, here's the lesson. Strength is only impressive when you've got something to push against. Gravity makes that possible. It's the invisible opponent that makes us look strong or weak. Without it, even the strongest human alive would look kind of floppy. Astronauts know it. That's why they train so hard to fake gravity's role in space. Because once you lose that daily resistance, strength fades faster than you'd think. And if we bring Superman into the mix, that's where things flip again. He doesn't need gravity to look strong. His strength is so over the top that he can push against anything, even empty space, by sheer willpower. That's why he can fly. Olympic lifters need gravity to show off. Astronauts lose it without gravity. Superman, he redefines the rules.
A black hole shows strength versus weight absurdity. All right, let's talk about the most unfair opponent in the universe. The black hole. You think gravity here on Earth is strong? Nah. Earth's gravity is like a friendly arm wrestling buddy compared to the absolute monster that is a black hole. Here's the deal. A black hole isn't just some big, heavy thing floating in space. It's a collapsed star, squished into such a tiny spot that its gravity goes absolutely insane. Imagine taking something like our sun, which is already massive, and cramming all that mass into an area smaller than a city. The result? A gravity well so powerful that once you cross the edge, what scientists call the event horizon, you're not coming back. Not you, not your spaceship, and not even light itself. And this is where the whole strength versus weight idea becomes hilarious. On Earth, you can resist gravity with strength. You can hold up a dumbbell, jump off the ground, maybe even launch a rocket if you've got the fuel. But with a black hole, forget it. You could be the strongest human, the strongest machine, or even Superman himself. If you get too close, that's it. Game over.
No amount of pushing, pulling, or lifting can save you. Gravity wins. Here's why. It's not about how heavy you are or how strong your muscles are. It's about escape velocity, the speed you'd need to break free. On Earth, that number is around 11.2 kilometers per second. With a rocket, that's doable. But near a black hole, the escape velocity is faster than the speed of light. And since nothing in the universe can go faster than light, it's literally impossible to escape. Your strength isn't even in the equation. It's like trying to arm wrestle a hurricane. Now, imagine what happens if you try. If you were falling feet first toward a black hole, your legs would feel a much stronger pull than your head, because gravity changes drastically over short distances there. This scientists call this spaghettification. Yeah, it's exactly what it sounds like. You'd get stretched out like a noodle, long and thin, until every atom in your body is ripped apart. Not exactly the kind of workout you want to sign up for. And here's the kicker. This isn't some sci-fi exaggeration. Astronomers have seen stars wander too close to black holes and get shredded. Entire suns ripped apart like paper, just gone. If a star can't win against the black hole's pull, you can be sure your gym routine isn't going to cut it either. But now, let's sneak Superman into the chat. In comics, he sometimes does wrestle with black holes. He can hover near the edge, resist the pull, and even break free. That's pure fiction, of course, but it highlights the whole idea of Superman science. To survive something like a black hole, you'd need a strength that isn't just physical. You'd need to defy the very laws of physics. And that's why black holes make the perfect example. They remind us that strength is powerful. But gravity? Gravity sets the ultimate rules of the game.
Gecko climbing physics. All right, let me blow your mind for a second. You've seen geckos, right? Those little lizards that can walk up walls and even hang upside down on glass like it's nothing? And every time you see it, the question just pops up. How the heck are they doing that? Are they tiny Spider-Men? Now, here's the truth. Geckos don't beat gravity by brute force. They're not secretly lifting their body weight with Hulk muscles in their toes. Nope. What they're doing is way smarter. It's straight-up physics wizardry. Their toes are covered with millions of tiny little hairs called setae. But wait, it gets crazier. Each of those hairs splits into even tinier endings called spatulae. So small, they're measured in nanometers. That means a single toe has an entire microscopic forest of sticky fibers. When those spatulae touch a surface, glass, wall, ceiling, you name it, they get close enough for something magical to happen. Van der Waals forces. Okay, fancy word, but here's the simple version. At the atomic level, every surface has a tiny electrical field around it. If you get something close enough, like the spatulae on a gecko's toe, there's a weak attraction between the molecules. Normally, it's so small you'd never notice. But when you multiply that weak attraction by millions and millions of spatulae, suddenly it's strong enough to hold the gecko's entire body against gravity. Here's the wild part. Scientists tested it and found that, in theory, a single gecko could hang from the ceiling using just one toe. That's how crazy effective this microscopic stickiness is. And yet, it's not glue. It's not suction. It's literally just physics at a molecular level doing all the work. The gecko can peel its toes on and off super quickly, which is why it can run across walls without getting stuck like tape. So what's happening here? The gecko isn't lifting itself against gravity. It's bypassing the weight problem completely. Instead of asking, how strong do I have to be to climb this wall? It's more like, how can I hack the surface so gravity doesn't matter? And boom, van der Waals forces for the win. And you know what's crazy? Scientists are trying to copy this. They're developing synthetic gecko tape, a material that sticks like a gecko's foot, but without glue. Imagine gloves or boots that let you climb up skyscrapers like Spider-Man. That's not sci-fi anymore. That's actual lab research happening right now. So the next time you see a gecko casually chilling on your wall, think about it. That little lizard isn't fighting gravity with brute strength. It's using one of the weakest forces in physics, multiplied 1,000,000 times, to completely ignore the rules. That's not strength. That's strategy.
Ants are super strong. All right, let's talk ants. You've definitely heard people say, ants are so strong they can carry 50 times their own body weight. And it's true. Imagine if you could throw your car over your head like a backpack. That's basically what an ant does every single day. But here's the catch. Ants aren't defying gravity. They're not born with little insect superpowers. They're just playing by the rules of physics, rules that actually make being small a major cheat code. So, what's going on here? It all comes down to something called scaling laws. Let's keep it super simple. When you shrink an object, whether it's a building, an animal, or a human, its volume and weight shrink much faster than its surface area and muscle cross-section. Translation? The smaller you are, the less your body weighs compared to how strong your muscles are relative to that weight. Think of it this way. If you take a cube and double its size, the volume and weight increases 8 times. But the surface area and strength capacity only increases 4 times. That means as things get bigger, their strength doesn't keep up with their weight. But as things get smaller, like ants, the opposite happens. Their strength stays too big compared to their tiny weight. So the ant carrying the giant crumb isn't flexing like a mini Hulk. It's just that gravity doesn't have much to pull on because the ant is so small. Now, flip that around. If humans followed the same scaling law and you suddenly shrunk down to the size of an ant, you'd feel insanely strong. You could pick up stuff dozens of times your body weight, leap around like Spider-Man, and basically live life as a superhero. But if you scaled an ant up to the size of a human, guess what? It wouldn't be strong at all. It would collapse under its own weight because its muscles wouldn't scale up fast enough to support its body. So the whole super strong ant thing isn't about ants being little bodybuilders. It's about gravity and strength scaling differently at small sizes. Gravity feels weaker the smaller you get, not because it actually changes, but because your muscles don't have as much weight to fight against.
And here's the fun twist. This is exactly why insects can do wild things like walk up walls or survive falls from ridiculous heights. If you drop an ant off a skyscraper, it won't splat. It just drifts down like a feather and keeps walking. Meanwhile, humans, yeah, not so lucky. So the next time you see an ant carrying a breadcrumb 5 times bigger than its head, don't think of it as Superman in miniature. Think of it as physics showing off. Small creatures don't beat gravity with strength. They beat it with size.
Elephants can't jump. Did you know elephants are the only mammals on Earth that cannot jump? That's right. The largest land animal alive today, with legs the size of tree trunks, can't even pull off the simplest trick your dog does every time you get home. But why? You'd think with all that muscle, they'd be able to spring off the ground like a massive pogo stick. The problem isn't that they're weak, it's that gravity hits them differently. Remember scaling laws from the ant story? Well, the bigger you are, the worse the trade-off gets. Here's the science in simple terms. An elephant's weight increases way faster than the strength of its muscles and bones. Sure, it has massive muscles, but those muscles are mostly busy just holding its body upright and moving it around. They don't have much extra power left over for explosive jumps. On top of that, their bones aren't built like springs. They're built like pillars, strong for support, but not elastic for bouncing. Now compare that to smaller animals, cats, kangaroos, even rabbits. They've got spring-loaded tendons and lighter frames, so when they push against the ground, their strength-to-weight ratio works in their favor. A rabbit can hop 5 times its body length, while an elephant can barely trot without looking like it's shaking the earth. So when an elephant tries to jump, here's what happens. Their front feet might lift off the ground, or their back feet might lift, but never all 4 at the same time. Gravity has basically locked them down. They're just too heavy to get airborne. And here's the funny part. Being unable to jump isn't really a problem for elephants. They don't need to escape predators with quick hops. They rely on sheer size and weight to stay safe. No lion is going to look at an elephant and think, yeah, I'll take that on. The elephant doesn't need agility. It has massive strength used for defense, not for defying gravity. If you want a what-if moment, imagine if elephants could jump. First of all, it would look terrifying, a 6-ton animal bouncing around like a kangaroo. But second, the Earth would actually feel those jumps as tiny quakes. Their landings would hit with the force of small explosions. Nature knew what it was doing when it said, nope, elephants, you stay grounded. So, while ants cheat gravity by being small, elephants lose against gravity by being too large. Their strength isn't weak, it's just matched perfectly for carrying their weight, not overcoming it. Birds escape gravity with wing strength. Let's talk about birds. They make it look so effortless, don't they? You're standing outside, maybe holding a sandwich, and a pigeon swoops down, takes a crumb, and then just lifts off like gravity doesn't even apply to it. Meanwhile, you try jumping as high as you can, and you're back down in less than a second. So how are birds pulling off this cheat code against gravity? The answer is simple but fascinating. It's not really about being light, it's about muscle strength and how they use it. Birds fight gravity with wings,
And those wings aren't just for gliding, they're powered by massive chest muscles. In fact, if you've ever eaten chicken or turkey, the breast meat you're chewing on, that's basically the engine room of flight. Those muscles are ridiculously strong for their size, built to flap fast and hard enough to push against the air. Here's where the magic happens. When a bird flaps downward, its wings generate lift. It's like pushing on the air the same way you'd push on water while swimming. The stronger the push, the more air pressure difference they create, and the more upward force they get. This upward lift is what cancels out gravity's pull. Now, notice something interesting. It doesn't matter if the bird is light or heavy, it matters how powerful its wing muscles are compared to its weight. That's why some birds can't fly at all. Chickens, for example, can flutter around a bit, but their bodies are too heavy and their muscles aren't strong enough to keep them airborne for long. On the other hand, hawks and eagles, they've got the muscle-to-weight ratio nailed down, so they can soar for hours. Think about hummingbirds for a second. These little guys are insane. Their wings flap so fast, up to 80 times per second, that they can literally hover in place like tiny helicopters fueled by sugar water. That's not being light, that's pure muscle endurance working overtime to keep them floating against gravity. And here's the kicker. Even big birds like albatrosses, which can weigh over 20 pounds, still conquer gravity. How? By combining wing strength with smart aerodynamics. They use long, wide wings to catch air currents, but they still need that initial burst of muscle power to get off the ground. It's the same reason airplanes need massive engines to lift into the sky before they can cruise. So when you see a bird flying, don't just think, oh, it's light. Nope, what's really happening is a non-stop gym workout in those chest muscles. It's strength in action. Every single flap, fighting gravity, one wing beat at a time. Meanwhile, if you strapped wings to a human, no matter how big, without the muscle strength to flap them at the right speed and power, you wouldn't go anywhere. Gravity would laugh and slam you right back down. Birds don't get a free pass from gravity. They just have the strength to weight balance tuned perfectly to escape it.
Giraffes have high blood pressure. All right, let's talk about giraffes. You see them at the zoo, all calm and elegant, like they don't have a care in the world. But inside that long neck of theirs, it's a full-on battle against gravity every single second. And the enemy, not just keeping their bodies standing upright, nope, it's about getting blood all the way up that skyscraper neck to their brains. Here's the thing. The taller you are, the harder it is for your heart to pump blood up against gravity. And giraffes, they take this to the extreme. Their necks can stretch up to 6 feet long, which means their poor hearts have to push blood way uphill. Imagine trying to pump water through a hose that's standing straight up and twice your height. That's basically what their circulatory system is doing 24/7. Now, how do they solve this? With super-powered hearts. A giraffe's heart isn't just big, it's insanely strong. It can weigh up to 25 pounds and generate blood pressure that's twice as high as a human's. We're talking about levels of pressure that if a human had it, doctors would panic and rush you to the ER. But for giraffes, that's just normal Tuesday biology. And here's where it gets crazier. That high pressure is needed not only to get blood up, but also to keep it from rushing back down. When a giraffe bends its head to drink water, gravity wants to flood the brain with too much blood, which could be deadly.
To counter this, giraffes have built-in check valves in their blood vessels and special vein structures that act like brakes, controlling the flow so their heads don't explode like a cartoon balloon. It's basically an engineering marvel. Their circulatory system is like a combination of a high-pressure pump and a hydraulic regulator. If Superman needed to drink from a lake while upside down, he'd need a system like this just to survive it. Now, let's zoom out. What does this tell us about gravity? It's not just pulling on the outside of things, it's literally shaping how animals evolve on the inside. The giraffe had to engineer its body to fight gravity's constant tug-of-war on its blood. Without that extreme heart strength, a giraffe's brain simply wouldn't get the oxygen it needs. And that's the beauty of it. Gravity doesn't care how tall you are, but if you want to push your limits, you'd better have the strength to back it up. In the giraffe's case, that strength is inside its chest, pounding away at ridiculous pressure just to keep it standing tall and thinking straight. So, next time you see a giraffe casually munching leaves, remember, what looks peaceful on the outside is actually a superhero-level strength battle against gravity happening inside every single second.
Astronauts lose muscle. All right, let's picture this. You're an astronaut. You've trained for years. You're strapped into a rocket, and boom, you're in space. Floating around like you're living in a zero-gravity dream. No more lugging heavy groceries. No more aching back from standing too long. No more falling flat on your face when you trip. Sounds awesome, right? But here's the twist. Nobody talks about when you first imagine space life. The very thing that makes floating so fun is also the thing that makes you weak. See, on Earth, gravity is basically your personal trainer. Every single step you take, every time you stand up from a chair, every time you carry your phone in your pocket, it's a mini workout against gravity. Your muscles are constantly firing even when you don't realize it. You're literally training 24/7 just by living under Earth's pull. But in space, that invisible gym vanishes. Suddenly, your muscles don't have to work to hold you up. Your legs aren't pushing against the ground. Your back isn't keeping you upright. And even your heart doesn't have to pump as hard to move blood around. It's like your body realizes, hey, why keep all this heavy-duty strength if I don't need it? And so, it starts cutting corners. That's why astronauts in space lose muscle and bone mass fast. We're talking up to 20% of muscle strength in just a couple of weeks if they don't work out. Their bones get weaker too, because bones also respond to gravity's constant stress. No load, no need to stay strong. It's efficiency for the body, but it's terrifying for humans who want to come back to Earth in one piece. This is why, if you've ever seen videos of astronauts on the International Space Station, you'll notice they spend hours every day on treadmills and resistance machines. Not for fun, not to get ripped, but just to not crumble like wet spaghetti noodles when they get back to Earth. Here's the part that blows my mind. It means that the strength you take for granted, the fact you can stand up, walk around, or lift your arm without thinking about it, isn't just yours. It's actually a partnership with gravity. Gravity challenges you, and your muscles answer back. Remove the challenge, and your body gets lazy real quick.
So, in a way, gravity is kind of like that tough coach you had in school, the one who never let you skip practice. You might hate it sometimes, but it's the reason you can perform at all. Without gravity pushing down on us every second, we'd all end up weak, fragile, and soft. Astronauts come home and often can't even walk properly for days. They have to relearn how to exist under gravity again. That's how dependent we are on this invisible force to keep us strong. So next time you sigh about how heavy your backpack feels, or groan about carrying groceries up the stairs, just remember, those little battles are actually what keep your body alive, tough, and ready. Without gravity, you'd lose the strength you didn't even know you had.
Tree height is limited. All right, let's play a little thought game. Imagine a forest where trees are so tall you can't even see the tops. You crane your neck, you squint, but the branches just disappear into the clouds. Sounds magical, right? But here's the crazy truth. There's actually a hard cap on how tall a tree can grow. Not because the tree doesn't want to, but because gravity says, nope, that's high enough. See, trees don't have little pumps inside them like a skyscraper with plumbing. They don't have motors to push water up from their roots to their leaves. Instead, they rely on a combo of capillary action, cohesion, and evaporation. Big words, but it's actually a beautiful system. Here's how it works in plain English. When water evaporates from the leaves, a process called transpiration, it pulls more water upward like a straw. The water molecules stick to each other, cohesion, and also kind of cling to the sides of the tiny vessels inside the tree, capillary action. So, little by little, the tree lifts gallons of water from its roots to the very top. But here's the snag. Gravity is always pulling down on that water column, and as the tree gets taller, it gets harder and harder to keep the straw unbroken. Once you get past around 120 to 130 meters, physics just taps the brakes. The tension needed to keep pulling water upward would cause the water column to snap like a rope that's stretched too far. That's why the tallest trees on Earth, like the mighty coast redwoods in California, max out around that limit. The tallest one we've ever measured, named Hyperion, is about 115 meters tall. Beyond that, it's basically impossible to keep water flowing up to the top leaves. They just dry out and die, no matter how much sunlight or soil nutrients the tree had. Think about that for a second. Gravity is literally drawing a line in the sand and saying, you can grow, but only up to here. It's like nature tried to make skyscraper trees, but physics shut it down. And here's the kicker. If gravity were weaker, say you planted the same tree on a smaller planet, trees could grow taller. If gravity were stronger, though, even our redwoods would be shorter. In other words, the trees we see today are perfectly shaped by Earth's gravity. So the next time you're standing under a giant redwood or a towering eucalyptus and you feel tiny, remember this. You're looking at nature's ultimate balancing act, where strength, water, and gravity are playing tug of war. And gravity always wins in the end.
Frogs can be levitated with magnets. Okay, get ready for one of the weirdest science experiments you'll ever hear about. Imagine walking into a lab, and instead of test tubes or microscopes, you see a frog just floating in midair. No strings, no invisible platforms, just hovering there like it's in zero gravity. Sounds like something out of a magician's act, right? But nope, this is real physics. Back in the late 1990s, a physicist named Andre Geim, fun fact, he later won a Nobel Prize, actually pulled this off. He and his team used an insanely powerful magnet to levitate a living frog. And the frog wasn't harmed. It just bobbed gently in the magnetic field, probably wondering what on earth was happening. So how does this work? Here's the mind bender. Even though we don't think of living creatures as magnetic, all biological tissue is made mostly of water. And water has a property called diamagnetism. That means when you put water in a strong magnetic field, the molecules try to push away from it. It's a super weak effect, so in everyday life you never notice it. But if the magnet is powerful enough, it can generate enough force to counteract gravity. And since frogs, like us, basically water balloons with legs, the whole animal is affected. So when Geim cranked up the magnet, the diamagnetic force lifted the frog off the ground, perfectly balancing the pull of gravity. The result? A floating amphibian, weightless without being in space. Now, before you get too excited, no, you can't just grab a fridge magnet and make your pet levitate. The magnets used here were on the order of 16 Tesla or more. That's hundreds of thousands of times stronger than the ones holding up your grocery list. These are the same kinds of magnets you'd find in particle accelerators or advanced MRI machines. Still, this experiment blew people's minds because it showed something profound. Gravity isn't unbeatable. If you apply the right kind of strength, whether it's magnetic, mechanical, or even biological, you can tip the scales. And frogs aren't the only ones. Scientists have levitated water droplets, peanuts, and even living mice using the same principle. It also makes you think, if magnets can levitate frogs here on Earth, could we one day use magnetic fields to simulate artificial gravity in space stations, or even make hover technology a reality? The science is there, but the engineering challenge is huge. But admit it, knowing that somewhere out there a frog once floated in a lab because magnets out-muscled gravity makes the world feel a little more like a comic book. Babies can hold their own weight. Here's a fun fact that might surprise you. A newborn baby, that tiny, fragile-looking human who can't even hold their head up straight, is actually strong enough to hold their own body weight with just their hands. No kidding. If you put your finger in a newborn's palm, they'll grab on like their life depends on it. And that's not just cute. It's science. This is called the palmar grasp reflex. Every baby is born with it. You can test it yourself. Place your finger across a newborn's palm, and boom, they clamp down like a little vice grip. For the first few months of life, this reflex is so strong that babies can literally hang by their hands. Of course, nobody's recommending you go testing this by dangling a baby off a pull-up bar, but doctors have actually studied it, and it's wild. So why would evolution give babies this hidden superpower? Think about our ancestors, way before cribs and strollers. Imagine early humans, or even pre-human primates, living in trees. For a baby to survive, it had to cling tightly to its mother as she climbed, walked, or even ran. If the baby didn't have a strong grip, well, let's just say natural selection would have taken its course. That don't let go grip was literally life or death. What's fascinating is that this grip reflex is automatic. It's not something the baby decides to do. It's wired into their nervous system, like a pre-installed survival program. Over time, as babies grow and develop voluntary motor control, the reflex fades, usually around 5 to 6 months old. By then, they don't need that cling-for-your-life strength because they're learning to sit, crawl, and eventually walk. And here's the fun way to think about it. If you're holding a newborn and they squeeze your finger, that's not just them being cute. It's their ancient survival coding saying, "I'm not letting go of you, no matter what." In a way, it's one of the first real connections they make with the world. So yeah, babies might look weak, but hidden in that tiny little body is the kind of strength that once kept entire generations alive. Makes you look at that innocent grip a whole lot differently, doesn't it?
Hummingbirds' wings beat 80 times per second. All right, let's talk about one of the craziest little powerhouses in the animal kingdom, the hummingbird. These tiny birds are basically nature's helicopters. While most birds flap their wings up and down, a hummingbird's wings move in a figure-8 pattern at insane speeds, around 80 beats per second. That's so fast your eyes can't even track it. You just see a blur, like a living drone. Now, here's the cool part. Gravity is pulling on hummingbirds just like it pulls on us. The difference is, these little guys fight back with pure strength and endurance. Every single wing beat is a battle against falling. Think about it. Hovering in place is way harder than just gliding or flapping forward, because the bird has to generate continuous upward lift without a break. It's like holding a push-up position without ever resting, except the hummingbird is doing it hundreds of times per second. And it's not just brute force, it's crazy efficiency. Their wings rotate at the shoulder joint, letting them push air down on both the forward and backward stroke. So unlike most birds, they're basically creating lift twice as often, double the force to keep them floating like magic. Of course, strength like that comes with a price. A hummingbird's metabolism is through the roof. Their hearts can beat over 1,200 times a minute just to fuel those tiny muscles. To keep that strength up, they eat like maniacs, slurping nectar all day, sometimes consuming more than their own body weight in food. Imagine if you had to eat your entire body weight in pizza every day just not to collapse. That's a hummingbird's daily grind. But here's the part I love. All this strength isn't about being big, it's the opposite. The hummingbird's secret weapon is its small size combined with insane muscle control. If they were the size of a crow, their wings would snap from the stress. It's physics working perfectly at a miniature scale, letting them do something no other bird can pull off. So the next time you see a hummingbird just hanging there in midair, sipping nectar like it's nothing, remember, what you're really seeing is a non-stop battle against gravity powered by one of the strongest muscle-to-weight ratios in the animal world. Tiny bird, massive strength story.
Soldiers in fighter jets black out if their heart strength can't overcome gravity. Okay, let's get real about what happens when humans go head-to-head with gravity. Imagine you're a fighter jet pilot pulling a hard turn at Mach speed.
The jet banks, the G-forces spike, and suddenly gravity doesn't feel like gravity anymore. Instead of 1 G, the normal pull you feel just standing here on Earth, your body might be slammed with 7, 8, even 9 Gs. That means everything in your body feels 7 to 9 times heavier. Sounds wild, right? But here's the dangerous part. Your blood is included in that weight. Under those insane G-forces, your blood doesn't want to stay evenly pumped around your body anymore. It starts pooling in your legs and lower body, away from your brain. And here's the brutal reality. If your heart isn't strong enough to push that heavy blood back up against gravity's pull, your brain gets starved of oxygen. The result? You start losing vision, like someone dimming the lights on you. It's called tunnel vision, or gray out. Push it further, and boom, you're unconscious. Fighter pilots call it G-LOC, or G-force-induced loss of consciousness. And it doesn't matter how tough you are physically. If your cardiovascular system can't generate enough force, gravity literally knocks you out. Now, to fight back, pilots don't just rely on their hearts alone. They train their bodies to squeeze blood upward, doing a special anti-G straining maneuver, which is basically tensing every muscle in their legs, abs, and chest to keep blood from pooling. They also wear G-suits, inflatable gear that literally squeezes their lower body when G-forces spike, helping the heart keep blood moving to the brain. Think about how crazy that is. Strength here isn't about lifting weights. It's about whether your heart and muscles can outmatch gravity pulling your blood down. Gravity becomes the ultimate opponent, not in holding you down, but in stealing consciousness right out of under your nose. So yeah, Superman might leap tall buildings in a single bound, but real fighter pilots, they fight gravity every time they turn their jet, battling to stay awake while their body is screaming to shut down. That's next-level strength. And a reminder that gravity doesn't always win with weight. Sometimes it wins by just yanking your blood in the wrong direction.
Pole vaulters convert speed to height. Okay, let's talk about pole vaulting. You've probably seen it in the Olympics. An athlete sprints down a track with this ridiculously long pole, plants it in the ground, bends it like it's made of rubber, and then somehow launches themselves several meters into the air, flying over a bar that looks impossible to clear. At first glance, it looks like sheer strength, as if the vaulter is muscling their way up into the sky, fighting gravity with raw power. But here's the trick. They're not fighting gravity in the way you might think. They're actually playing a clever game of energy transformation. Here's what's really happening. When the athlete sprints down the runway, they're building up kinetic energy, the energy of motion. Think of it like charging a battery, but with speed instead of electricity. All that forward momentum isn't wasted. It's stored and redirected. The pole acts like a spring. When the vaulter jams it into the box at the end of the runway, the pole bends under their weight. That bend isn't just for show. It's absorbing the runner's horizontal energy. Now, physics has a rule. Energy doesn't disappear, it just changes form. So as the pole straightens back up, it returns that stored energy to the vaulter, but this time it's pointing upward instead of forward. In other words, the athlete isn't muscling their way against gravity. They're converting the energy they built up on the ground into vertical lift. Gravity is still there, pulling them down the whole time,
But the vaulter cleverly redirects their momentum into a new direction, almost like tricking gravity into letting them rise for a moment. Here's the wild part. If you slowed the whole thing down, you'd notice that the vaulter's arms and core aren't lifting their entire body into the sky. Their muscles are mostly steering and controlling the pole, not providing the energy to get them airborne. The strength here isn't raw pushing against gravity. It's the ability to handle insane forces, keep balance, and time their body movement perfectly so that the pole snaps back and launches them upward at just the right moment. Think about it like this. Imagine you're on a trampoline. If you just stand there and try to jump high using only your leg muscles, you'll barely get anywhere. But if you time it right and let the trampoline stretch and snap back, suddenly you're soaring higher than your muscles alone could ever manage. That's what pole vaulters are doing. Except instead of a stretchy trampoline, it's a fiberglass pole. And instead of bouncing, they're redirecting forward speed into vertical flight. The best part? This is basically Superman science in disguise. If Superman wanted to leap tall buildings like in his early comic days, he wouldn't need to squat and muscle his way up. He could, in theory, sprint at high speed, use his strength to control some kind of flexible material, or maybe even the ground itself if he was strong enough to dent it, and redirect his forward momentum into vertical launch. It wouldn't just be brute strength. It would be clever physics, the same physics pole vaulters exploit. And here's a fun little experiment you can imagine. If a pole vaulter had somehow infinite sprinting speed with the perfect pole that never snapped, in theory, they could launch themselves to insane heights, way beyond Olympic records. Of course, in reality, things like air resistance, pole strength, and human muscle limits cap the performance. But the underlying point is this. Pole vaulting proves that gravity isn't beaten by being stronger than it. It's beaten by understanding how energy moves and how you can transform one kind of strength, running fast, into another form, rising high. So next time you see a pole vaulter soar into the air, remember, they're not defying gravity. They're redirecting their own momentum, turning horizontal speed into vertical height, and letting physics do most of the heavy lifting.
Deadlifts test gravity resistance. All right, let's talk about one of the most primal displays of human strength, the deadlift. If you've ever stepped into a gym, you've probably seen someone step up to a barbell loaded with so many plates it looks like the floor might crack. They bend down, grip the cold steel, take a deep breath, and then, against all odds, they stand up with it. That's the deadlift. It's raw, it's simple, and it's basically the ultimate test of how much you can resist gravity. Now, here's what makes the deadlift so fascinating. It's not about how tall you are, how big your body is, or even how fast you can move. It's purely a battle between your muscles and the force of gravity. When you load up a barbell with, say, 200 kilos, gravity is pulling that weight straight down toward the earth with relentless force. There's no trick, no clever momentum shift like in pole vaulting, no wing lift like in birds. It's just you, your muscles, and gravity saying, let's see what you've got. And here's the cool part. Body size alone doesn't guarantee success. Sure,
Bigger people often have more muscle mass, which helps. But deadlifting isn't a body weight contest. Some of the best deadlifters in the world aren't the tallest or the heaviest. They're the ones who have trained their muscles, tendons, and nervous system to generate insane amounts of force. Think about it this way. Gravity doesn't care if you're skinny or bulky, short or tall. It just pulls with the same acceleration. Your job is simply to provide enough upward force to match and then overcome that pull. When you grab that bar and start the lift, a lot of things happen at once. Your hands grip tight, your forearms tense up, your back locks in like a steel beam, and your legs drive into the floor with everything they've got. It's almost like trying to push the earth down with your feet while pulling the bar up. And the crazy part? That's literally what you're doing. Every action has an equal and opposite reaction, so when you push into the ground during a deadlift, the ground pushes back, allowing you to overcome gravity's grip on the barbell. What makes deadlifting so raw and pure is that there's no way to cheat gravity here. You can't trick it with technique like in some lifts, and you can't use momentum like swinging a kettlebell. Either your muscles are strong enough to move that bar, or they're not. That's why the deadlift is sometimes called the king of lifts. It's not flashy, it's not complicated, it's just the most honest test of raw strength against gravity's pull. And here's something interesting. When people see a massive deadlift, they often assume it's all about muscle. But a huge part of it is actually neurological. Your brain and nervous system have to recruit as many muscle fibers as possible, all firing in perfect coordination to generate that explosive upward force. That's why trained lifters can pull far more weight than someone untrained, even if they're the same size. Strength isn't just about big muscles. It's about teaching your body how to fight gravity more efficiently. Think about how ancient humans might have done this. Long before barbells and gyms, people were lifting heavy rocks, logs, and animal carcasses. It wasn't for sport, it was survival. That primal act of bracing your body and heaving something off the ground is hardwired into us. The deadlift we know today is basically a modern way of testing an ancient skill. How much weight can you make stand up against gravity before your body says, nope? And of course, when you get into record-breaking territory, it gets wild. The heaviest deadlift ever officially recorded is over 500 kilograms. That's literally lifting a small car off the ground. Think about how absurd that is. Gravity is pulling half a ton straight down, and one human's muscles, tendons, and willpower are enough to resist that. It's the ultimate demonstration of just how far training and adaptation can push the human body. So the next time you see someone deadlifting in the gym, don't just see it as a person picking up a heavy bar. See it as a raw, ancient battle between muscle and gravity, stripped of all tricks and shortcuts. It's not about size, it's not about speed, it's pure strength, resisting the most constant, relentless force we know, gravity.
High jumpers clear 8 feet. At first glance, the high jump almost looks like someone is cheating gravity. I mean, think about it. A human being with no wings, no pole, no trampoline, somehow manages to fling their body more than 8 feet into the air. That's higher than most ceilings in a normal house. If you saw someone do it out of context, you'd think they were superhuman. But here's the twist. It's not that high jumpers are somehow stronger than gravity. They're just masters at using physics to their advantage. The secret is that the high jump isn't really about jumping upward.
If you watch closely, the run-up is just as important as the leap. High jumpers sprint toward the bar with serious speed, and that horizontal velocity is the foundation of everything that follows. When they hit the takeoff point, they drive one leg into the ground and redirect a big chunk of that horizontal momentum into vertical lift. It's less about brute force pushing against gravity and more about clever redirection of energy. But the real magic comes in with technique, especially the Fosbury flop, which completely revolutionized the sport in the 1960s. Before Dick Fosbury came along, jumpers used to try hurdling over the bar feet first, or with a scissor kick style. It worked, but it wasn't efficient. Fosbury realized something mind-blowing. If you arch your back and go over the bar head first, upside down, your center of mass, the point physics uses to measure your body's weight, actually passes under the bar, even though your body clears it. That's the key trick. You don't need to get your whole body's center of mass above the bar. You just need to contort yourself so parts of your body clear it, while your overall center of mass stays lower. It's like bending the rules of motion without breaking them. Gravity is still pulling you down the whole time, but by combining speed, timing, and body positioning, high jumpers buy themselves just enough airtime to twist over heights that look impossible. Another way to think of it is when you throw a rock, it follows a parabolic arc. The rock doesn't fight gravity. It just rides the path of motion until gravity brings it back down. High jumpers are basically doing the same thing, except they're the rock, and they've learned how to manipulate their body mid-flight to maximize what little airtime physics allows. Their leap isn't about muscle versus gravity, so much as it is motion versus timing. What makes this even cooler is that the human body has limits. The takeoff leg can only generate so much force against the ground, and gravity isn't going anywhere. Yet, by bending the rules with technique, athletes have managed to push the high jump world record to jaw-dropping levels, over 2.45 meters, about 8 feet. That's not beating gravity. That's working with motion and clever biomechanics to squeeze every ounce of performance out of the laws of physics. So, the next time you watch a high jump, don't just see it as someone leaping impossibly high. See it as a dance with gravity, where speed turns into height and technique turns the impossible into just barely possible. They're not stronger than gravity. They're just bending the game of motion to their favor.
Parkour athletes manipulate gravity. If you've ever seen a parkour video, you know it looks like people have somehow hacked reality. They're running up walls, flipping across rooftops, vaulting over rails, and landing from insane heights like gravity barely exists. But here's the thing. They're not breaking the laws of physics. They're actually some of the best at obeying them. What parkour athletes do so well is manipulate gravity, using their body's strength with pinpoint precision to redirect forces instead of just smashing against them. Let's break this down. When you jump off something, gravity is going to pull you down, no questions asked. You can't stop it. But what you can do is control how that landing force gets distributed through your body. A beginner might jump off a wall and just land stiff-legged, which means all the force slams straight into their joints. That's how you get hurt. A trained traceur, that's what parkour practitioners call themselves, though, will roll on landing, spreading the impact over time and distance. Same gravity, same weight, but instead of one big destructive thud, the energy gets bled off smoothly. That's strength combined with smart technique. And it's not just about landing. Look at how they climb walls. A normal person might try to brute force it, just grabbing the top and hauling themselves up. A parkour athlete, on the other hand, runs up the wall, using momentum to carry their center of mass higher before pulling up. They're not necessarily stronger than you or me in raw muscle terms. They just understand that if you redirect your body's weight and time your push right, you can make gravity work with you instead of against you. Think about vaults over rails. It looks effortless, like they're floating. But what's really happening is a constant conversation between strength, timing, and gravity. Push too early and gravity punishes you by dragging you down before you clear the obstacle. Push too late and you smash into it. But nail the timing and it's like your weight just flows over the rail. That's why parkour training emphasizes repetition over and over, because the human brain and muscles have to learn how to redirect those forces perfectly. And here's something wild. Parkour isn't about raw power the way weightlifting is. You don't need to squat 500 pounds to be good at it. What you need is body control. The kind of precision strength that lets you know exactly how much force to put in and at what angle. It's like a constant balancing act. Too much and you over-rotate. Too little and you crash. That precision is what makes it look like parkour athletes are defying gravity. So when you watch someone sprint across rooftops, leap a 10-foot gap, and land like a cat, remember, they're not superhuman. They're humans who've mastered the art of manipulating gravity's pull. They don't fight weight head-on. They redirect it, flow with it, and use strength in just the right places to make the impossible look casual. Gravity never goes away, but in parkour, it becomes more like a dance partner than an enemy.
Rock climbers rely on grip strength. Picture this. You're halfway up a cliff face, nothing beneath you but open air, and the only thing keeping you alive is the strength of your fingertips pressing against a crack or clinging to a little nub of rock no bigger than a coin. Sounds impossible, right? But that's the everyday reality for rock climbers. They've learned how to turn their grip strength into something powerful enough to counteract their entire body weight. And honestly, when you think about it, that's kind of superhuman. Let's put this into perspective. The average person might be able to hang from a pull-up bar for 20, maybe 30 seconds before their fingers give out. That's gravity working full force, dragging every pound of your body down. But elite climbers, they can dangle from their fingertips on a ledge the size of a credit card. Some even train with hangboards, pieces of wood with tiny little cutouts, where they just hang on with the very tips of their fingers for minutes at a time. Imagine all your weight pulling downward and your body saying, "Nope, not today, gravity." And here's the fascinating thing.
Climbers don't beat gravity by being huge or bulky. In fact, the best climbers often look pretty lean. Why? Because climbing isn't about brute force. It's about strength to weight ratio. A massive bodybuilder might be way stronger overall, but his extra bulk is just more weight for gravity to pull down. Meanwhile, a lighter climber with crazy strong fingers can hang on to vertical walls like a gecko. It's not about size, it's about efficiency. Think about the physics of it. When a climber pulls on a tiny hold, their fingers are converting muscular strength into counterforce against gravity. If your body weighs 70 kilograms, that's about 700 newtons of force pulling you straight down. Your fingers, tiny little muscles and tendons, have to match that force or you fall. And yet, with training, they do. The skin, tendons, and even bones in a climber's fingers adapt to handle insane loads. That's why their hands often look gnarly, chalk-covered, calloused, sometimes scarred. Those are battle marks from their daily war with gravity. And it's not just grip strength, it's technique. Climbers learn to use their feet, shift their balance, and keep their body close to the wall so gravity's pull doesn't feel as strong. But when it comes down to it, when they're hanging off an overhang or pulling through a tough move, it's those fingers that save the day. Even just one slip can mean the difference between sticking the climb and falling. If you think about it, it almost mirrors the superhero fantasy. We imagine Spider-Man sticking to walls with web powers. But real-life climbers are doing something almost as crazy with nothing but skin, chalk, and raw grip strength. No webs, no superpowers, just their fingers taking on their entire body weight and saying, "We got this." So next time you see a climber clinging to a cliff that looks completely impossible, remember, what you're watching is the ultimate showdown of gravity versus grip. And in that moment, 10 tiny fingers are enough to tell gravity, "Not today."
Parkour athletes manipulate gravity. If you've ever seen a parkour video, you know it looks like people have somehow hacked reality. They're running up walls, flipping across rooftops, vaulting over rails, and landing from insane heights like gravity barely exists. But here's the thing. They're not breaking the laws of physics. They're actually some of the best at obeying them. What parkour athletes do so well is manipulate gravity, using their body's strength with pinpoint precision to redirect forces instead of just smashing against them. Let's break this down. When you jump off something, gravity is going to pull you down, no questions asked. You can't stop it. But what you can do is control how that landing force gets distributed through your body. A beginner might jump off a wall and just land stiff-legged, which means all the force slams straight into their joints. That's how you get hurt. A trained traceur, that's what parkour practitioners call themselves, though, will roll on landing, spreading the impact over time and distance. Same gravity, same weight, but instead of one big destructive thud, the energy gets bled off smoothly. That's strength combined with smart technique. And it's not just about landing. Look at how they climb walls. A normal person might try to brute force it, just grabbing the top and hauling themselves up. A parkour athlete, on the other hand, runs up the wall, using momentum to carry their center of mass higher before pulling up. They're not necessarily stronger than you or me in raw muscle terms. They just understand that if you redirect your body's weight and time your push right, you can make gravity work with you instead of against you. Think about vaults over rails. It looks effortless, like they're floating. But what's really happening is a constant conversation between strength, timing, and gravity. Push too early and gravity punishes you by dragging you down before you clear the obstacle. Push too late and you smash into it. But nail the timing and it's like your weight just flows over the rail. That's why parkour training emphasizes repetition over and over, because the human brain and muscles have to learn how to redirect those forces perfectly. And here's something wild. Parkour isn't about raw power the way weightlifting is. You don't need to squat 500 pounds to be good at it. What you need is body control. The kind of precision strength that lets you know exactly how much force to put in and at what angle. It's like a constant balancing act. Too much and you over-rotate. Too little and you crash. That precision is what makes it look like parkour athletes are defying gravity. So when you watch someone sprint across rooftops, leap a 10-foot gap, and land like a cat, remember, they're not superhuman. They're humans who've mastered the art of manipulating gravity's pull. They don't fight weight head-on. They redirect it, flow with it, and use strength in just the right places to make the impossible look casual. Gravity never goes away, but in parkour, it becomes more like a dance partner than an enemy.
Olympic gymnasts hold iron crosses. If you've ever watched Olympic gymnastics, there's one move that always makes the crowd go silent: the iron cross on the rings. The athlete lowers his body into a perfect T shape, arms stretched straight out, body rigid, and just holds it. No wobbling, no swinging, just pure control. It looks simple enough, like he's just holding himself up, but in reality, it's one of the most brutally difficult strength feats in all of sports. Why? Because it's literally a human being using nothing but muscle power to resist gravity's constant pull on their entire body. To understand how hard it is, imagine hanging from a pull-up bar. Now, instead of letting your arms hang naturally, try holding them perfectly horizontal while suspending your entire body weight beneath them. The torque generated on the shoulders is insane, up to 7 times body weight pressure on the joints. And unlike a deadlift, where you can plant your feet and use momentum, the iron cross offers no leverage, no trick, no cheat. It's raw isometric strength. Every fiber in the shoulders, chest, lats, and arms has to fire at maximum capacity just to keep gravity from winning. That's why even elite weightlifters, people who can squat hundreds of pounds, often can't hold an iron cross for a single second. It's not about lifting a barbell.
It's about fighting physics directly. Gymnasts train for years to master this. They start with resistance bands to reduce the load, slowly building tendon strength and joint stability. The rings themselves add another layer of difficulty because they're not fixed, they wobble. That instability means the athlete has to use dozens of tiny stabilizing muscles to stay balanced. Gravity isn't just pulling them down, it's constantly trying to twist them out of position. That's why the Iron Cross isn't just strength, it's strength plus control plus balance, all in one terrifyingly difficult package. What makes this so mesmerizing is how quiet the strength looks. A strong man lifting a giant barbell grunts, strains, maybe screams, but a gymnast in an Iron Cross looks calm, almost effortless, face relaxed, body steady. It's the ultimate illusion, like gravity simply stopped working on them. But behind that illusion is years of pain, thousands of hours of training, and a body forged to resist Earth's pull in one of the most extreme ways imaginable. Here's the kicker. The Iron Cross isn't even about moving against gravity, it's about not moving. That's what makes it so different from jumps, lifts, or throws. It's static defiance. Gravity is saying, "Come down now," and the gymnast replies, "No, not yet." For a few seconds, the human body becomes something close to superhuman, an immovable object suspended in space, held aloft by nothing but willpower and muscle fibers. So the next time you see a gymnast calmly holding an Iron Cross, don't be fooled by the stillness. What you're actually watching is a battle with gravity at its most pure and unforgiving. And for those few seconds, muscle alone is winning.
Martial artists break bricks. We've all seen that jaw-dropping moment in martial arts demos. A person raises their hand, focuses for a second, and then smashes a stack of bricks or wooden boards like they're made of paper. The crowd goes wild, jaws drop, and someone inevitably whispers, "Wow, that guy must have insane strength." But here's the twist. It's not really about brute force. Martial artists aren't superhumanly strong. They're masters at using physics, especially gravity and momentum, to make it look like magic. Let's break it down. If you just slap a brick with your hand, chances are you'll walk away with a bruised palm and 0 broken bricks. That's because a casual hit spreads energy across a wide area, and the brick absorbs it. But martial artists do something different. They channel all their strength and weight into a focused strike. They don't just swing their arm, they drop their entire body's mass into the hit, redirecting gravity itself. It's like dropping a sledgehammer instead of swinging a stick. Same principle, way more power delivered. Here's where it gets cooler. Breaking a brick isn't about stopping at the surface. A rookie hits the top of the brick and thinks that's the goal. But a trained martial artist imagines striping through the brick, sending their force past it into the table or ground beneath. By aiming beyond, their energy keeps traveling, and the brittle material in the middle can't withstand the sudden shock. That's why you'll often see them break multiple bricks at once. It's not that their hand is harder than concrete. It's that their technique makes the brick brittle against the force of gravity plus momentum working together. And let's not forget speed. Strength alone won't do it.
A slow push won't break anything. But when you move fast, you increase momentum. And momentum multiplied by gravity is devastating. That's why tiny martial artists, people who might weigh 120 pounds, can shatter bricks while someone twice their size can't. They're not fighting gravity with muscle. They're syncing with it, redirecting it downward in an explosive, laser-focused burst. There's also a mental side. Before the strike, martial artists calm their breathing, focus their eyes, and tighten their core. This isn't just for show. It primes their body to transfer energy as one unified machine. Without that mental preparation, you'd hesitate, and hesitation means pulling back some of the force. Ever notice how they often yell a kiai when they strike? That shout isn't just dramatic flair. It tightens the body at the exact moment of impact, maximizing the force delivered and ensuring gravity isn't wasted. So the next time you see someone split bricks with their bare hands, don't think of it as a freak display of superhuman strength. Think of it as physics in action. Speed plus focus, momentum plus gravity, precision plus mindset. It's less about having the arms of a superhero and more about knowing exactly how to let the earth itself help deliver the blow. In other words, martial artists don't just hit hard, they hit smart.
Ski jumpers float. Picture this. You're standing at the top of a snowy hill, skis strapped to your feet, heart pounding. You look down and see a ramp that seems to launch straight into the sky. Most of us would probably freeze right there, imagining ourselves tumbling headfirst into a snowball of embarrassment. But ski jumpers, they lean forward, push off, and suddenly they're not just falling, they're floating. For a few glorious seconds, it's like they've cheated gravity itself. But how on earth is that possible? They're not birds, they don't have wings. Yet somehow these athletes manage to glide through the air like human rockets. Here's the trick. It's all about aerodynamics. The second a jumper leaves the ramp, gravity wants to yank them straight down. That's non-negotiable. But instead of surrendering to that pull, ski jumpers use clever body positioning to generate lift, kind of like how airplane wings work. When they lean forward and spread their arms and skis into a V shape, the air moving over their body and equipment creates a pressure difference. The air above is moving faster, while the air below creates higher pressure. Boom! Instant lift. They can't escape gravity, of course, but they can delay its full effect by balancing it out with aerodynamic forces. Think about it like this. You've probably stuck your hand out the window of a moving car, right? If you angle your palm flat, the wind smacks against it and pushes it back. But if you tilt your hand just right, suddenly it rises almost like it's floating on the air. That's exactly what ski jumpers are doing, except instead of going 60 miles per hour down a highway, they're flying down a ramp at nearly 100 kilometers per hour with their whole body acting like a wing. The crazy part is that the difference between sinking like a rock and soaring like a bird comes down to posture. If they lean too far back, they catch drag and lose distance. If they lean too far forward, they nosedive into the snow. They have to hit this sweet spot, just enough lift to stretch their air time, but not so much drag that they slow down. It's a razor-thin balance, and that's why ski jumping is as much about precision and timing as it is about bravery. And here's where gravity still gets the last laugh. No matter how good they are, no matter how much lift they generate, the skier will always come back down. That's the deal with gravity. It never lets go. But those few seconds of floating are enough to cover mind-blowing distances. Some jumpers soar more than 250 meters through the air. That's longer than 2 football fields back to back, all because they know how to trick the air into working with them instead of against them. So the next time you see a ski jumper glide like a superhero in slow motion, remember, they're not beating gravity, they're negotiating with it. They borrow a little help from the air, balance their weight just right, and for a few heart-stopping seconds, they get to experience what it feels like to fly. It's not strength, it's not magic, it's science, skill, and gravity playing a high-stakes game of tug-of-war.
Acrobats balance by micro-adjustments. Imagine watching a circus acrobat walking across a thin wire, suspended high above the ground. The crowd gasps, kids cover their eyes, and you can almost feel your palms getting sweaty just looking at them. To us, it seems impossible. How can a human body stay upright on something barely wider than a thumb? It looks like sheer magic. But the truth is, every second that acrobat is up there, their body is waging a constant, invisible war with gravity. Here's what's happening. Gravity is trying to pull them straight down, the same way it pulls on all of us. The difference is that on solid ground, we don't notice how often we sway, shift, or adjust. But on a thin rope or a bar, every tiny movement matters. Acrobats survive up there not because they're perfectly still, but because they're never still. Their muscles are constantly firing, tiny corrections in the ankles, knees, hips, and even the core, adjusting their center of mass to stay directly above the wire. Think of it like standing on one leg. At first, you might think you're steady, but if you really focus, you'll notice your foot twitching, your ankle rolling slightly, your torso shifting. Those are micro-adjustments. On the ground, they keep you from falling sideways. On the wire, those same adjustments are the difference between grace and disaster. Strength plays a huge role here, not in some dramatic lifting weights sense, but in endurance. The leg muscles, especially the calves and thighs, are burning the whole time, holding tension against gravity's constant pull. The core muscles act like shock absorbers, keeping the torso from tipping over. Even the arms aren't just out for show. When they stretch them wide, it increases their rotational inertia, making it harder for gravity to topple them quickly. It's the same principle that makes a spinning figure skater slower when their arms are extended. The fascinating part is that acrobats don't just rely on raw strength. They rely on sensitivity and awareness of every shift in their balance. They can feel the rope sway on their feet, feel their body tilt by just a few degrees, and instantly respond. It's not about overpowering gravity. It's about dancing with it, constantly correcting the imbalance before it snowballs into a fall.
In fact, if you've ever seen one hold a handstand on a chair balanced on another chair, stacked on yet another, you'll realize just how precise this game of micro-adjustments is. Gravity is relentless, but strength, control, and tiny, nearly invisible movements let acrobats hold their ground against gravity's pull. They're not defeating gravity, they're outsmarting it one twitch at a time.
Bridges don't fight gravity. When you look at a massive suspension bridge, like the Golden Gate or Brooklyn Bridge, it almost feels like it's defying gravity. Dozens of cars, trucks, and buses rumble across it every minute, yet the whole structure seems to float effortlessly in the air. But here's the secret. Bridges don't resist gravity head-on. Instead, they're masterpieces of engineering that redirect gravity's pull into forms of strength that materials can handle best: tension and compression. Think of it this way. Gravity is always pushing down. If a bridge tried to simply hold up that weight by brute force, the structure would crumble under its own mass. Instead, engineers design bridges so that gravity's downward pull is spread out and transformed. The cables in a suspension bridge, for example, aren't just hanging there. They're under extreme tension, pulled tight like guitar strings. Every car that drives across causes those cables to stretch slightly, but the strength of steel keeps them from snapping. That tension is then transferred to the towers, the tall vertical structures rising from the water. Those towers don't resist by pulling. They resist by being compressed, pressed downward into the earth. Materials like stone, concrete, and steel are incredibly good at handling compression, meaning they can withstand being squashed by enormous forces. Gravity tries to pull the bridge down, but instead of breaking it, the bridge channels that force through tension in the cables and compression in the towers straight into the ground. It's almost like judo, using your opponent's force against them instead of meeting it with raw strength. The bridge doesn't beat gravity. It guides it safely into the earth. That's why some bridges can last for hundreds of years, carrying unimaginable amounts of weight every day without failing. Different bridge designs use the same principle in creative ways. An arch bridge is shaped so that the load pushes outward and downward, forcing the arch into compression. That's why Roman stone arches have survived for millennia. They're perfectly designed to let gravity press the stones tighter together. A truss bridge distributes forces across triangular patterns, each piece either stretched in tension or squeezed in compression, never trying to resist gravity in ways materials aren't good at. What makes this even more fascinating is that bridges grow stronger the more they use gravity correctly. The heavier the load on an arch, the tighter the stones press together, making collapse less likely. Gravity, The very thing trying to pull everything down becomes a stabilizing ally once properly redirected. So when you cross a bridge, remember, it isn't a war between steel and gravity. It's a negotiation. The bridge says, "Go ahead, pull down as much as you like. I'll just send your force where I'm strongest." And that's why those giant spans stay standing, calmly carrying the weight of the world, day after day. Skyscrapers sway. When you look up at a skyscraper, say the Burj Khalifa in Dubai or One World Trade Center in New York, you might think the entire structure is an immovable wall of concrete and steel, stubbornly fighting against gravity's pull. But the truth is, skyscrapers don't just rely on brute strength to stay upright. They actually sway. And that sway is not a flaw. It's the secret to their survival. Gravity constantly drags the weight of a skyscraper downward, and that alone requires enormous structural strength. But the real danger doesn't usually come from gravity. It comes from wind. At hundreds of meters in the air, winds can push against a tower with forces strong enough to topple anything too rigid. If engineers built skyscrapers stiff and unbending, they would crack and collapse under those lateral forces. Instead, engineers designed them to bend. Think of a skyscraper less like a solid wall and more like a giant reed in the wind. When a storm blows, the building sways gently back and forth, distributing the force instead of resisting it all at once. Some of the tallest towers can sway a few feet at the very top. That movement is imperceptible when you're inside, but it's enough to absorb the energy of the wind without breaking. The same principle applies to earthquakes. A stiff, brittle structure shatters under sudden shocks. But a flexible skyscraper can absorb and redirect that energy, keeping the whole building standing. Engineers sometimes even install tuned mass dampers, giant counterweights suspended near the top floors. These act like pendulums swinging opposite the sway of the building to cancel out the motion. One famous example is in Taipei 101 in Taiwan, where a 660-ton golden sphere hangs like a colossal pendulum, keeping the skyscraper stable against typhoons and earthquakes. What's remarkable is that flexibility doesn't make a skyscraper weaker, it makes it stronger. By allowing gravity and wind to push, the building survives forces far greater than raw strength alone could withstand. It's the same principle martial artists use in judo. Don't fight force directly, redirect it. So the next time you see a skyline filled with towering giants of steel and glass, remember, those buildings aren't just blocks of material defying nature. They're carefully tuned instruments, swaying in rhythm with the Earth's forces. Skyscrapers don't conquer gravity and wind, they dance with them.
Satellites orbit by falling. Okay, here's a question for you. Have you ever thought about why satellites don't just drop straight out of the sky? Like, Earth is pulling on them all the time, right? Gravity doesn't suddenly turn off once you reach space.
So why don't they just plummet down the moment they're launched? The answer is both simple and mind-blowing. Satellites aren't defying gravity. They're actually falling constantly. The trick is, they're falling sideways so fast that they keep missing the Earth. Let's break this down in everyday terms. Imagine throwing a baseball. If you throw it gently, it arcs and hits the ground a few feet away. Throw it harder. It travels farther before hitting the ground. Now, imagine if you could throw that baseball so hard it curves with the Earth itself. Instead of ever reaching the ground, it just keeps circling the planet. That's literally what a satellite is doing. It's the same ball, just moving at thousands of kilometers an hour. So here's the wild part. Satellites are not outside of gravity's grip at all. In fact, the International Space Station, which looks like it's peacefully floating in orbit, is still under about 90% of Earth's gravity compared to what we feel here. Astronauts inside aren't weightless because gravity is gone. They're in freefall. The whole ship and everyone inside it is falling at the same rate, giving that floating effect. Think about riding a roller coaster at the top of a hill where you feel your stomach drop. That feeling of being weightless is the exact same principle, just stretched out for months at a time. The ISS is like the ultimate never-ending roller coaster ride, except instead of screaming for 2 minutes, astronauts are calmly eating space food while orbiting Earth every 90 minutes. And here's where the strength versus gravity idea gets fun. When you hear about rockets fighting gravity, it's not like they're punching upward until they finally break free. They're not breaking out of gravity's cage at all. They're just building up enough sideways speed so that when they do fall, they fall around the Earth instead of into it. Gravity is always the referee, and the rocket's job is just to cheat sideways fast enough that it never actually lands. So next time you see pictures of satellites or even GPS signals helping you find your favorite taco place, remember this: none of those satellites are floating freely. They're constantly plummeting toward Earth at incredible speed, but they're so fast, the ground keeps curving away beneath them. It's not escape. It's just a never-ending fall. A cosmic game of miss the ground.
Dams resist gravity's water pressure. When you look at a dam, say the Hoover Dam or the Three Gorges Dam, it can feel like just another giant wall of concrete. But here's the thing. These structures aren't just walls. They're humanity's answer to one of gravity's most relentless side effects, water pressure. See, water doesn't just sit quietly. Gravity is constantly pulling it downward, and that creates pressure that pushes sideways against anything in its way. The deeper the water, the stronger the pressure. For every meter you go down, the pressure builds higher and higher. At the bottom of a huge reservoir, that pressure is like an invisible giant leaning against the dam with unimaginable force, trying to push it over. Now imagine billions of gallons of water stacked up behind one structure. That's what a dam holds back.
And it's only possible because engineers design them to work with physics, not against it. Gravity tries to crush or topple the dam, but the dam's shape and strength redirect those forces downward into the Earth's bedrock. That's why most big dams curve inward toward the water. The weight of the water actually helps press the dam into its foundations instead of ripping it apart. It's a clever jujitsu move against gravity, using its own force to maintain stability. And here's a staggering perspective. The Hoover Dam alone holds back over 9 trillion gallons of water. The weight of that water is so massive that if the dam weren't perfectly designed, the collapse wouldn't just be a spill, it would be a cataclysm. Entire cities downstream would vanish in minutes. This is why dams are not built casually. They are monuments to our ability to create structures strong enough to resist gravity's endless pull on water. Here's where the strength versus gravity battle really comes into focus. The concrete in a dam isn't just sitting there like a passive block. It's actively resisting the sideways pressure caused by gravity dragging water downward. The dam doesn't cancel gravity, it just redirects its consequences. Strength here isn't about being stronger than gravity itself. It's about designing a system that channels those forces safely into the ground. So, the next time you see a massive dam, don't just think of it as a water reservoir or a power plant. Think of it as a giant arm wrestling match between gravity and human engineering. Gravity constantly says, "This wall should collapse." The dam replies, "Not today. I'm stronger." Elevators counterbalance weight. Think about the last time you stepped into an elevator. You press a button, the doors close, and the cabin glides upward effortlessly, carrying not just you, but maybe a dozen other people. It feels smooth, simple, almost casual, as if the elevator barely notices the hundreds or even thousands of pounds it's lifting. But here's the trick. The elevator isn't muscling you upward against gravity at all. It's cheating the fight. The secret lies in the counterweight system. Every elevator car is paired with a giant weight, usually hidden in the shaft behind the scenes. That counterweight weighs almost as much as a fully loaded elevator. So when the motor pulls on the cables, it's not dragging the elevator up from scratch. It's just tipping the balance one way or the other. In effect, it's like a seesaw. Instead of brute forcing against gravity, the system redistributes weight, so the motor only has to overcome the difference between the car and the counterweight. This makes elevators incredibly efficient. Imagine trying to lift a car engine with your bare hands. Impossible. But now, imagine if someone handed you a perfectly balanced scale, with the engine on one side and a nearly equal counterweight on the other. Suddenly, you wouldn't need superhuman strength. Just a little nudge could move the engine upward. That's exactly what the elevator motor does, and why it doesn't need to be monstrously powerful to move tons of steel and passengers. Here's where the gravity strength lesson comes in. Elevators don't defeat gravity, they outsmart it. Gravity is pulling down on both the elevator car and the counterweight equally. By balancing the two, engineers cancel out most of the heaviness, leaving the motor to handle only the imbalance. That's why modern skyscrapers, with hundreds of floors, can move people up and down all day without requiring endless amounts of energy or hulking machines. And here's a fun fact: the counterweight doesn't just save energy, it makes the ride safer. If the elevator cable ever snapped, a rare but terrifying thought, gravity wouldn't send the car plummeting like in the movies. Safety brakes would lock it in place, and the counterbalance ensures that even in failure, gravity doesn't win outright. So, when you step into an elevator tomorrow, realize this: the reason you glide upward so smoothly isn't because the motor is monstrously strong. It's because centuries of engineering found a clever way to balance gravity with strength, turning what should be an impossible lift into something effortless. In short, elevators don't fight gravity with brute force. They beat it with brains.
Rockets don't push Earth. When you watch a rocket launch, it looks like a showdown between sheer power and the immovable pull of Earth. The rocket roars, flames explode downward, and the vehicle slowly, almost reluctantly, lifts off the pad. At first glance, you might think the rocket is pushing against the ground or shoving itself away from the planet. But the truth is stranger. Rockets don't push against Earth at all. They win by producing a force greater than gravity itself. Here's how it works. Earth's gravity is always pulling everything toward its center. For something as massive as a rocket, hundreds of tons of metal, fuel, and cargo, that downward pull is enormous. To break free, the rocket needs to generate a force upward that's even stronger than that pull. That force is thrust, created by Newton's third law of motion. Every action has an equal and opposite reaction. When the rocket's engines expel exhaust gases downward at blistering speeds, the rocket itself is shoved upward in return. Think about it like this. Gravity is holding the rocket hostage, chaining it to the launch pad. The engines don't negotiate. They brute force their way out, pouring fire and pressure downward until the upward reaction exceeds the downward weight. Once the thrust surpasses gravity's grip, the rocket begins its slow, epic climb toward the sky. But here's the fascinating twist. The rocket doesn't push against the air, or the launch pad, or the ground beneath it. It pushes against nothing at all. Even in the vacuum of space, where there's no air to push on, rockets still work perfectly. Why? Because thrust comes from expelling mass at high velocity, not from leaning on the environment. That's why astronauts can fire small thrusters in the emptiness of orbit and still change direction. They're not pushing against space. They're pushing against their own exhaust. This tug-of-war between thrust and gravity defines the entire journey. At launch, almost all of the rocket's fuel is burned just to escape Earth's pull. More than 90% of its total mass is fuel alone. Once free of the atmosphere and gravity's strongest grip,
movement becomes much easier. The rocket doesn't have to keep burning furiously forever. It just needed to win the opening battle. So the next time you see a rocket ascend, remember, it isn't battling the Earth itself. It's battling an invisible force that never stops pulling. And by creating thrust greater than that pull, it proves that even gravity, the force that rules our lives, can be overcome with enough strength. In short, rockets don't push against Earth. They push against themselves, and that's how they escape.
Hovercrafts use air strength. Imagine a massive machine gliding effortlessly across land and water, skimming like a puck on ice. That's a hovercraft. At first glance, it almost looks like it's defying gravity, floating above the surface without touching it. But in reality, a hovercraft doesn't escape gravity at all. It cleverly cheats it using the strength of compressed air. Here's how it works. A hovercraft has huge fans underneath that force air downward into a flexible skirt, a kind of rubber curtain around the base. Instead of letting that air immediately escape, the skirt traps it, creating a sealed cushion. This cushion builds up pressure until it's strong enough to lift the entire craft off the ground. Not high, just a few inches, but enough to break contact. Think about the force involved. The weight of the hovercraft pushes down due to gravity. To counter this, the trapped air must push up with equal strength. That upward force is called lift from pressure. Just like a balloon presses against your hand when inflated, the air under a hovercraft presses against the ground, and the ground pushes back, holding the vehicle aloft. This design solves a fundamental problem: friction. Traditional vehicles rely on wheels or tracks, which always press into the surface and create resistance. A hovercraft avoids this by never truly touching the surface it travels over. Whether it's land, mud, ice, or water, the craft rides on its own cushion of air. Gravity still pulls it down, but the air's strength distributes that weight evenly, allowing smooth, almost frictionless movement. But there's a catch. Unlike an airplane, which slices upward with wings and maintains altitude, a hovercraft is always leaking. The pressurized air constantly escapes from under the skirt, so the fans have to keep pumping more air to maintain lift. It's a delicate balance. Stop the fans, and gravity instantly wins, bringing the craft back to the ground. The genius of the hovercraft is that it doesn't need to overcome gravity completely like a rocket. It only needs to match gravity's pull enough to stay slightly above the surface. This makes it perfect for terrains where wheels or boats struggle, such as swamps, frozen rivers, or flood zones. So when you see a hovercraft gliding as if weightless, don't be fooled into thinking it's floating like magic. It's still a prisoner of gravity, but it's using the invisible strength of air to trick the ground into holding it up. In short, hovercrafts don't fly, they hover.
and their strength lies in turning air into a cushion powerful enough to resist gravity.
Magnets beat gravity. If you've ever seen a maglev train, it almost looks like something out of science fiction. A 100-ton machine hovering silently above the tracks, gliding forward without touching the ground. To the casual observer, it seems like these trains are breaking one of nature's hardest rules, gravity. After all, how can something so heavy just float? The secret isn't magic. It's magnetism, a force that, when strong enough, can counteract gravity's constant pull. Magnets generate invisible fields that either attract or repel other magnetic materials. And unlike gravity, which only pulls, magnets can push with just as much strength as they pull. If you've ever tried to press the same poles of two magnets together and felt them float apart, you've experienced the same principle that keeps maglev trains aloft. Here's how it works. A maglev system aligns extremely powerful electromagnets along both the train and the track. By carefully controlling the magnetic fields, engineers create repulsion strong enough to lift the entire train several centimeters above the rails. Gravity is still tugging downward with massive force, but the magnets push upward with equal strength, canceling it out. The result? The train levitates. And here's where the genius really shows. With no wheels touching the rails, there's almost zero friction. The only resistance left is air itself. That's why maglev trains can reach breathtaking speeds of over 600 kilometers per hour, faster than most airplanes during takeoff. It's not just about speed either. The ride is smooth, silent, and efficient, because the battle against friction has been won by magnetic strength. But the real marvel isn't floating, it's the stability. A levitating train sounds like it should wobble or fall off, but magnetic control systems are so precise that they can keep hundreds of tons of steel perfectly aligned at insane speeds. Gravity constantly tries to pull the train down, but the field strength doesn't just match it, it adjusts in real time, keeping balance every millisecond. This isn't limited to trains. Scientists have used the same principle to levitate frogs, droplets of water, even small pieces of metal by placing them in extremely powerful magnetic fields. In each case, gravity is still there, pulling as always. But the magnets generate a counterforce so strong it completely overrides the weight of the object. So while humans will never truly turn off gravity, magnets prove that another force of nature can rival it head-on. With enough field strength, even the heaviest machines can float as if gravity never existed. In short, magnets don't just resist gravity. In the right setup, they beat it, letting trains and objects hover in plain sight.
Helicopters hover. Okay, picture this for a second. You're standing on the ground, looking up at a helicopter that's just hanging there in the sky. No forward motion, no wings gliding through the air, no visible strings holding it up. Just a big metal machine, somehow stuck in midair. Doesn't it almost feel like cheating? Like
Gravity's sitting there tugging on it with the same merciless force that pulls you and me to the ground. And yet this flying beast just shrugs and says, I'll stay here. Thanks. So, how in the world is that possible? The short answer is, helicopters can hover because the strength of their spinning rotors perfectly balances the downward pull of gravity. But to really get it, let's unpack it in a way that makes sense without a physics textbook. Gravity is the bully here. It pulls everything down with the same acceleration, about 9.8 meters per second squared. That means whether it's your keys, your phone, or a multi-ton helicopter, gravity is giving it the same tug toward the Earth. But here's the difference. The weight, how heavy something feels, depends on its mass. A helicopter can weigh several thousand pounds, so the pull downward is massive. It should, by all accounts, crash to the ground unless something is fighting back. That something is the helicopter's rotor blades. Think of them as giant spinning wings. Now, unlike airplane wings, which need forward motion to slice through air and generate lift, helicopter rotors spin fast enough that they create their own airflow. Each blade is shaped like an airfoil, curved on top, flatter underneath. When they whip through the air, they push air downward. And thanks to Newton's third law, for every action, there's an equal and opposite reaction. Pushing air down creates an upward push on the helicopter. So here's the balancing act. Gravity is pulling down with all its might. Rotor blades are pushing air down, which pushes the helicopter up. When those two forces are perfectly equal, the helicopter doesn't rise or fall. It just hovers. It's like a tug-of-war match, where both sides are pulling with the exact same strength. The rope doesn't move in either direction. But here's where it gets interesting. Hovering isn't easy mode for a helicopter. In fact, it's one of the hardest things for a pilot to do. Because it's not just about matching gravity once. You have to constantly adjust to keep that balance. Tiny shifts in wind, air density, or even how much fuel you've burned can change the weight and lift relationship. So the pilot is always, and I mean always, making micro adjustments on the controls. If you've ever tried balancing a broomstick on your finger, you know how it wobbles and you keep moving your hand to keep it upright. That's basically what hovering is like, but with thousands of pounds of machinery and life inside. And here's another mind bender. Helicopters don't just hover by brute force. They're not muscling gravity into submission. They're redirecting air. Think of it like standing in a swimming pool. If you push water down with your hands, your body floats up. It feels like you're defying gravity, but really you're just using another medium to push against. Helicopters do the same thing with air. They're not fighting gravity head-on. They're cleverly sidestepping it by pushing air in the opposite direction. Now, you might be wondering, if helicopters are so good at this, why don't airplanes just hover too? Great question. The difference is in design. Airplanes use big, fixed wings and rely on speed. The faster they go, the more air gets pushed downward and the more lift they get. Stop moving, and an airplane is basically a giant rock with wings. Helicopters, though, bring their own movement by spinning their wings really fast in circles.
That way, they can generate lift without moving forward. That's why a helicopter can land on a rooftop, rescue someone from a mountain, or hover over a traffic jam while the news crew films. But here's the fun twist. While hovering looks magical, it's super expensive in terms of energy. Those engines are working overtime to keep those blades slicing through air at insane speeds. A hovering helicopter burns fuel like crazy, way more than a plane cruising smoothly through the sky. It's a reminder that gravity is relentless. You can balance it, but it always comes at a cost. So next time you see a helicopter hanging in midair, don't just think, cool machine. Think about the invisible battle happening. Gravity yanking down with thousands of pounds of force, and rotor blades pushing air down just hard enough to cancel it out. It's like watching two titans locked in a dead-even arm wrestle, neither gaining ground. And maybe ask yourself this. If you could hover like that, just balance perfectly in midair, just floating 3 feet off the ground, chilling, sipping coffee, sounds awesome, right? But then remember, you'd be burning fuel like a helicopter, working overtime just to stay in one spot. Suddenly, sitting on the couch sounds not so bad after all.
Cranes multiply human strength. All right, let's play a little imagination game. Picture yourself standing in front of a skyscraper that's still under construction. You look up, way, way up, and there's this enormous steel beam dangling hundreds of feet in the air. The kind of beam that weighs more than a car. And what's holding it there? A crane. Just this tall, spindly-looking tower with an arm stretching out like it's casually holding a toy. Now pause for a second and ask yourself, if you tried to lift that beam with your bare hands, how far do you think you'd get? Yeah, nowhere. Maybe you could shift one end an inch before your back started screaming. So how is it that a crane can hoist something that no single human could even dream of budging? Did humans suddenly get stronger? Nope. What we did was cheat, beautifully. We invented ways to multiply our strength. That's what cranes are all about. They're not magical, gravity-defying machines. They're just the smartest extension of a really old idea. Mechanical advantage. Let's strip it down. Imagine you've got a big, heavy rock you want to move. If you try to pick it straight up, good luck. But if you stick a long stick under it and wedge the stick against a smaller rock, suddenly you can pry it loose with much less effort. That's a lever, one of the simplest machines humans ever invented. And cranes are basically levers, pulleys, and counterweights scaled up to a gigantic size. Think about the arm of a crane. It's like an ultra-long lever. On one side, you've got the load, that heavy steel beam. On the other side, you've often got counterweights, massive blocks of concrete. These counterweights balance out some of the load so the crane doesn't topple over. It's the same idea as balancing a seesaw at the playground. If one kid is way heavier than the other, the lighter kid needs to scoot farther back to even things out. That's leverage. Cranes just do it with steel beams and counterweights instead of kids. But lifting is only half the story. The other secret weapon cranes use is the pulley. A pulley is nothing fancy. It's just a wheel with a rope looped over it. But here's the clever trick. If you add more pulleys to your system, you can distribute the weight over multiple ropes. That means you pull with less force to lift the same weight. Imagine trying to haul a bucket of water straight up from a well. Tough, right? But if you run the rope over a pulley, suddenly you're pulling down, using your own body weight, and it feels way easier. Add more pulleys, and the effort drops even more. Cranes combine both ideas, the lever and the pulley, so a relatively small motor or human-operated control system can lift absurdly heavy objects. We're talking hundreds of tons. Gravity doesn't change. The beam still weighs the same. But we, through engineering, found a way to spread the load and make the job doable without needing a superhero. Now here's where I want you to really picture it. Imagine you're the operator, sitting inside that tiny cab near the top of the crane tower. It's hot, noisy, and you're basically controlling one of the strongest arms mankind has ever built. With a few small movements of your hands, you can swing an object that weighs as much as 50 elephants. Doesn't that feel wild? You're not stronger than gravity. You're just using clever tools to outsmart it. And here's the beautiful part. Cranes are a direct continuation of something humans have always done, using tools to extend our power. A caveman using a stick to pry something loose was doing the exact same thing you see on a modern construction site. The difference is scale. We went from lifting rocks to lifting entire sections of buildings, bridges, and even ships. Cranes are literally the reason cities look the way they do today. Without them, skyscrapers wouldn't exist. Neither would half the monuments, stadiums, or massive infrastructure projects we take for granted. But let's not forget, cranes come with risk too, because you're essentially playing tug-of-war with gravity on a massive scale. If a crane isn't balanced properly, if the load is too heavy, or if the wind catches the arm at the wrong angle, things can go south fast. You've probably seen news clips of cranes collapsing in storms or on job sites. That's gravity reminding us, hey, you're clever, but don't get cocky. So the next time you see a crane swinging something high above the city, don't just glance and move on. Think about what's really happening. A handful of simple principles, leverage, pulleys, and counterweights, all working together to make humans seem way stronger than we actually are. It's not brute force, it's strategy. And here's a fun thought to leave you with. If I handed you a rope and a pulley system right now, you could lift something way heavier than yourself. No superhero serum required. Cranes just take that little trick and crank it up to city-sized proportions. So in a way, every tower and crane you see is proof of this very human superpower. We don't beat gravity with strength, we beat it with brains.